All right, and this is where, starting in this video, this is where there's a little bit of hand waving, I'm going to be honest. It's a little bit of theoretical math, and I can go through the proof with anyone that's interested. But in the previous, when we developed the previous formula, when I was showing you on the other page, I had told you that making a right angle, if I put the center line through, that angle is theta, and this angle is theta. All right, now, when we do this, and this is where it becomes the theoretical math will walk in, and I can show you a simple proof to justify it. This green line is the capital L line from above, and we're talking about that as our theta m. So that's the difference between the two. Now, as or because, and this is where you kind of put a star in here, and this is what I can show you in class if you're interested, because theta is very small, so that's the one in blue, the one we used in the previous page. Because it is so small, because we're talking about such small angles, we can assume that theta is equal to theta m. So those two angles are actually equal, and that's just because of the very, very small angle we're actually dealing with. So therefore, we end up with sine theta equals xm over L. So there's another formula I'm going to go back and add to my page. And if I multiply both sides by d, and you'll see why when I go back to the other page, we end up with a formula like that, which gives us another formula with different information. We can add that to our formula sheet. So sliding back, we now have that sine theta equals xm over L, which is true for both sides. But because we put d sine theta equals d xm over L, it allows us then to draw the conclusion that m lambda, so from above, is also equal to d xm over L. Similarly, d sine theta equals d xm over L, which tells me that that phase shift of lambda is equal to d xm over L. So you can see the formulas, excuse me, are identical. It's just in destructive interference we have m plus 1/2 on the, instead of just an m. All right, put them out of phase. All right, where are we now? We got one last formula that we do want to talk about here, and that is m lambda equals dxm over L. So that's the one we just developed on the previous page. And what I want to do is I want to see if I can pull up a picture or a website to demonstrate Young's double slit. Actually, what I'll do is I'm going to post the link with this video so you can actually go and try the applet yourself and play with it, because it's always a little bit, you're going to take more from it when you get to play with it with the hands-on. So let's talk about this formula here. We know that m is just an integer value, lambda is our wavelength, and d is a constant, it's the distance between the slits. xm is your distance from our center line to bright region. Oops. Bright region. There we go. So what happens if I want to know the distance from one to the next? So for example, if we take a look at the screen, this is what I'm talking about here. So I have bright, dark, bright, dark, bright, dark. How far is it to the next bright fringe, or the next bright region? So I take that formula, m lambda, and what I'm going to do is, I know the next one will occur. So let's say this occurs at m, so I'm back down with my diagram again. This is going to be at m plus 1, the next bright region. So I'm going to do the difference between them two. So that means in brackets, I'm going to replace, I'm going to go to the far region first, so m plus 1 lambda. So I'm looking at the right side of my equation right now. And if I subtract m lambda. All right, I'm going to be able to find this distance right here. So if I do the same process to the right side, I know I'll have d and then subscript xm plus 1 over L, which is a constant, minus d xm over L. So I'm looking at the m plus first, the next bright region, subtracting the current one. When I go through and simplify here, so I'll use my distributive law to get rid of the brackets. So on this side, I'll have m lambda plus lambda minus m lambda. On the other side, I'm going to have d and L are constant. I'm going to common factor them out. And I'm left with x m plus 1 minus xm. So on this side, it's kind of nice. The m lambdas disappear. So I end up with a lambda d over L. And what I find inside the brackets, I can just describe this as delta x. And there is our final formula for Young's double slit. So delta x is the width of a band. Or your bandwidth. Surprise, surprise. All right, so going back to that first formula slide here, we end up with our formula, lambda equals d delta x over L, lambda equals d delta x, and it's the same formula if you want to find the next dark region, so it depends on what you're looking for. So very, very important here, make sure you label what each letter represents on your formula sheet, because it makes quite a difference if you have them in the wrong order. So again, I want you to make sure you go and try the formula or the applet for Young's double slit that I have listed. It's kind of neat. It shows the color bands and how you can change the widths and so on and so forth. So a couple of quick examples to finish off the note. Two identical sources, 5 centimeters apart. So that's providing me with my D value. Need to make sure you convert that to meters again, everything in SI standard. Operate at at 10 hertz. So we know a frequency. So I'm gonna write that down. At a point on the first nodal line, 10 centimeters from the source. So what we know is we have a dark region. That's what that's telling us. So we know our delta L, dark region, occurs at 0.1 meters. All right, so it's telling us the location where that's actually occurring. So to visualize it, here's your nodal line. So I'll draw in a black nodal line. And we have our 2 point sources located here and here. We know that the distance could be anywhere on this dark line, this dark region. There's your L1, there's your it'll be backwards, L2 and L1. We know that the delta L here is going to be 0.01 meters. It's that differential distance. That's what that information is providing. A point on the first nodal line is 10. Oh, sorry. That's where it comes from. It's telling us, I got to read the rest of the question. It tells us that L2 is 0.01. Oops, 0.1, sorry, meters. It tells us that L1 is 0.11 meters. So L2 minus L1 is the 0.01. I was jumping the gun there. Okay, so A part. The wavelength of the waves. The wavelength of the waves. So now you're trying to decide, you're looking for lambda. Lambda is the unknown in A part. So you got to figure out what information do I know. Well, I know D, I know F, I know delta L. Is there anything that will help me here? Well, I do have a formula that has delta L equals M plus 1/2 lambda. Now I know to use the destructive interference. So destructive interference, because it tells me that we are working with a nodal line. So as soon as you see nodal line in the question, we are using destructive interference. Information here, unless otherwise told, we're going to assume that M is equal to 1. All right, so unless they tell us that it is the, actually, my mistake, it is told to us right here, first nodal line. I just got to read my information a little bit closer. If it's the first nodal line, I'll add that information. We now know M is 1. If they don't indicate it in the question, I found with our textbook, you assume it to be 1 unless told otherwise. So now that we know all this information, it's just to simply put it into the equation and solve for the unknown. So we find that lambda is equal to 6.67 times 10 to the negative 3 meters. So keeping with our SI standard, I put it in scientific notation since that's what the calculator provided. Now we want to know the velocity of the waves. Well, for B part, V equals F lambda. It's the only formula we have that relates the two. So V equals 10 hertz multiplied by 6.67 times 10 to the negative 3. So in this situation, 6.67 times 10 to the negative 2 meters per second. All right. So because it's, you got to remember, it's introductory back to wave 3 of light. It's going back similar to a grade 11 course where you just got to find your right information, identify the right formula, and substitute it in. So it's going to be, the tricky part will be identifying that information. So next example, a source with a wavelength. So wavelength, 4.5 times 10 to the negative 7 meters, illuminates 2 slits that are that far apart. So I know my D times 10 to the 6 meters. So that's fairly significant distance apart, up in the area of what, 3 million meters apart. What's the angle at which the second order maxima occurs? So for A part, second order maxima means that we are looking for an angle, okay, because it says what angle, so that's the giveaway. Second order maxima means your M value will be 2. So here we are again. We're playing with information. We have to use a formula that uses sine theta because we need theta, and we know lambda and D. So you do a quick scan of your formulas, and you find that D sine theta equals M lambda. I'm using the constructive interference because we're looking at a maximum. And now I substitute in my information. So we have 3 times 10 to the 6th sine theta equals, our M is 2, lambda is 4.5 times 10 to the negative 7th. So theta equals our sine inverse of our information. And we find that theta is equal to 17.5 degrees. So second order maxima occurs when our angle is at 17.5 degrees. B part, what's the distance the second order maxima is from center line? So the key here, center line is a measurement of xm. And we still know all the information, but we need to pick a formula that uses the xm. So D xm over L. So once you scan your information, you're going to find that that's the one we're going to be looking at. I'm just going to rearrange it first. So xm equals M lambda times L over D. It's not necessary. You can substitute the numbers in. It's whatever you're more comfortable with. So we end up with 2. Lambda is 4.5 times 10 to the negative 7th. L. L's unknown. It's not given. And that's divided by 3 times 10 to the 6th. All right. Now, if you've done the calculations, I think what I've done wrong, just kind of looking at my note here, it looks like it should have been 3 times 10 to the negative 6th, the original question. So that's what my calculations, I think, are based on. So if you want to just go back through that first part up top, put a negative in, probably if you've used the calculator, you're trying to figure out what was I doing to get those numbers. And it looks like I see a star here that I should have used that. So doing that calculation, you get 1.6 M. And I'll finish up the last example very quickly in the last note or video.